We improve the robustness of world action models using mechanistic interpretability and inference time alignment via optimal control. WAMs perform generalizable robot action generation, but remain highly sensitive to small environmental changes. Minor shifts in camera position, robot pose, or object configuration can cause major performance degradation. We wish to improve robustness without extra training. We study how WAMs internally represent three common nuisance factors: changes in gripper position, camera position, and visual noise. For each nuisance factor, we compare activations from paired perturbed and unperturbed rollouts. We perform PCA on the resulting contrastive directions and use the leading components to evaluate if the two activation distributions are linearly separable. This separability is a key prerequisite for our steering methods, which assume that nuisance features are modulated by one consistent direction in activation space. Ultimately, we find that nuisance representations are highly dependent on the task and model architecture, and these mechanistic results help identify settings where activation steering is likely to be effective. For separable tasks, we extend two inference time steering methods to WAMs. The first is ActAdd, which computes the difference between perturbed and unperturbed activations and injects it into the model during inference to counteract the perturbation, steering the WAM towards its nominal behavior. The second method, WALQR, models the latent dynamics in a lower dimensional subspace and formulates steering as an optimal control problem that tracks a feature set point over the latent subspace. We evaluate our steering on improving WAM robustness to perturbations in the Libero 10 simulator environment. When nuisance features are separable in activation space, activation steering improves performance under perturbation and increases the robustness of WAMs without requiring additional training data, as shown under Gaussian noise perturbations for the Cosmos policy and DIT for DIT models, as well as camera perturbations for the Cosmos policy model. And initial gripper perturbations for Cosmos and DIT for DIT, all of which have consistent feature separability. Notably, our steering strategies can also generalize to new tasks. Using contrastive vectors for a nuisance feature extracted from a base task, such as Libero Task 0, we can apply the same steering strategy to improve robustness to that perturbation on a new Libero task. In contrast, when our mechanistic study shows poor separability, the steered and unsteered performance are similar, with some examples here. This indicates the efficacy of our mechanistic study in predicting steering success and motivates work in training more steerable WAMs. Overall, our results suggest that mechanistic interpretability can reveal actionable structure and steering directions in WAMs and enable targeted inference time interventions that improve robustness,